So, question 12. We've got y equals a to the x. We've got to show that dy by dx is a to the x ln a. Well, we can do this. We really can. It does not equal xa to the x minus 1. That's the classic blunder. It's because x is the constant is the base and the variable is the exponent this time, rather than how it normally is where the variable is the base and the constant is the exponent. So they've switched them. That's why it's got a different way of behaving when you differentiate it. Now, the easiest way to prove this, in my opinion, is to take logs of both sides, flick the power down, and then to differentiate implicitly. Yeah, so we're going to do d by dx to everything. Remember, d by dx is the same as d by dy times dy by dx, and this essentially tells us how to differentiate functions of y rather than functions of x. So let's do it. Differentiate this, you get 1 over y, but because we differentiate a function of y, we stick a dy by dx on the end. Differentiate a number times x, because a is just constant, so ln a is just constant. And what do you get? You get the number times x. Well, it's just going to differentiate to the number itself, times the y over. But of course, y is a to the x, and so we have our answer. So we get a to the x ln a. And it's done. Okay, so we've proved it, yeah? Okay, next part. Now, for the next part, think about what you've just shown. When you differentiate, like say 3 to the x, you get ln 3 times 3 to the x. So what this is telling you is things of the form a to the power of x, exponentials if you like, always differentiate to a constant times by themselves. Well, how are they going to behave when you integrate them? They're going to behave by doing the opposite to that, which is they're going to integrate to themselves divided by that constant, yeah? And plus c. And that means that this right-hand side would therefore differentiate back to the left-hand side. Okay, so knowing that, let's have a go at doing this. We're going to integrate between 2 and 1, 4 to the power of x dx. It's going to integrate to 4 to the x over ln 4 between 2 and 1. And that gives you 16 over ln 4. Ln 4 is, of course, 2 ln 2, just because ln 4 is ln 2 squared, and the 2 can come down. And the reason why I'm doing that is because of how they want the answer. Minus 4 over 2 ln 2. That's naturally 12 over 2 ln 2, which is the same as 6 times by ln 2 to the minus 1. So I guess k is 6 and n is minus 1. Okay, 13. Okay, I find these ones a little bit annoying, really. The log modelling ones are a bit, I don't know, I'm not that excited about them. Show that this relationship can be written like this. Well, just take logs of both sides. And I guess they want us to do it base 10. Now, the one thing you can get wrong here is flicking the power down too early. You must write the log law of add first. Yeah, multiplying, is adding, if you see what I mean, before you flick that power down. And there's a really good reason for that. If we had a m to the b written like that, then I'd let you flick the power down. But this is a times m to the power of b first, yeah? And so because we haven't got both sides to the power of b, we can't do that move first. Anyway, we can see that this is the way they want us to do it, because then it leads straight to their answer. And we've got it. Okay, so we've shown the relationship can be written like that. And then the student gathers data for the graphs of r and m and plots log r against log m. Here's log r against log m. Okay, we've got 2 points. Now remember, on this graph, your y coordinates are log r. Yeah, they've already been logged, and your x coordinates are log m. So the other thing I know as well is the gradient of this graph is b, and the y-intercept is log base 10 of a. So if I'm going to do this, bear that in mind. I can easily work out the gradient. I can say b equals 1.9 minus 1.2 divided by 1.8 minus 0.7. And that gives us 0.7 over 1.1, or 7/11. Cool. Did it want b exact? I've got to find a and b to 3 sig fig. I don't know what 7/11 is. Let me work it out. 0.636363. So let's say 0.636. Okay, for a, what I'm going to have to do is plug these in. Yeah. So let's plug in log r is 1.9. Log base 10 of a is what I want. B is 0.636. Let me just put the dots up there so I don't make a thing. And then log m is going to be 1.8 when log r is 1.9. We're just plugging a point in to find what a equals here. And then what do I get for log a? I'm just going to work this out. 1.9 minus 1.8 times 7/11. Let's work with the exact values. Okay, I'm now getting log base 10 of a is 0.75445454. And so a is going to be 10 to the power of that, because that's how you undo a logarithm. You get 5.68. And we've got a and b. And so clearly r equals 5.68 times by m to the power of 0.636. And you've done it. Okay, with reference to the model, interpret the value of the constant a. These can be quite tricky, yeah? This is a constant a. What does it really mean? Well, it's not the value at m equals, you can't use it as just, oh, that's going to be the value as m equals 0, because there's no time here. That's always 0.636. If the mass was 0, then r is going to be 0. Sorry, I've forgotten what r stands for. M is the mass, and r is the oxygen consumed per hour. Yeah, that's not what that represents. Yeah, because this isn't the variable up here this time. What it does represent, though, is you could say, well, if the mass of the animal was 1 gram, then oxygen consumed, what was R standing for again? I've already forgotten. Then oxygen consumed per hour would be 5.68. And that's all they need you to write. Let me just check out the units on that. It's the resting metabolic rate, isn't it? Yeah, the resting metabolic rate in milliliters. And that's all you need to put. Okay, so that's the log one done. Ah, good. Something I can get my teeth into, a substitution. Okay, right. I can't see the limits again, so I'm going to have to look them up. 1 second. Oh, it's in the second part that we have limits, but so we'll just do the first part first. Use the substitution, show that that is equal to that. Well, always differentiate your substitution first. Yeah, and we're going to get 1 differentiating to 0, and then sine squared x differentiates to, think of it as sine x all squared. It differentiates to 2 sine x. Oh, and you need to differentiate inside the brackets cos x. Yeah. Okay, so that's what we've got. Now, I'm very keen on this, of like trying to tidy it up almost over here. So we get 2 sine x cos x dx. Don't turn that into sine 2x. It's not actually that helpful to do that. And that's because I've got no double angles in the answer I'm going towards. I need to get this all in terms of u, yeah? And so, well, I suppose with tan x, that's like a sine x over a cos x. And so if I had instead, like, if I put this as like du over, because I want the dx, can you see that basically I've got here a dx over cos x here, or dx, sorry, a sine x dx here. And it might even be worth, okay, actually, maybe you won't see this. Maybe I'll do it the longer way. Okay, I'll do it the longer way. Okay, so what do we get? We get 8. I am going to write down the tan x as sine x over cos x, though. Over 1 plus sine squared x. Well, I really want to get this in terms of u, so I'm going to write it as in terms of u, multiplied by 2 sine x cos x dx. Yeah? Okay, great. Now what's going to happen here? The cos x's are going to cancel, and you're going to be left with 16, which I'm actually going to take outside the integral. And then can you see that you've got a sine squared x over u there? d. Right, and now what am I doing here? That should be, I apologize, I've done that wrong. That should be, sorry, because I'm trying to swap that dx for a du. And so I've got to put this on this side, really. I might have left the 2, yeah. Can I show you the way I would have done it? Because I don't like doing it this way. Let me show you. Definitely. Silly, silly, silly. The best thing you can do in these, if you ask me, think of that as 8 sine x dx, yeah? Well, I've got a 2, but why don't I turn this into 8 sine x dx? Yeah, so I'm going to times that side by 4. But I'm also going to move this over here, so it becomes 4 du. I have to times both sides by 4, obviously, over cos x, yeah? Now, the reason why I'm doing that is because I can see I've got an 8 sine x in here, yeah? And so this becomes, like, the 8 sine x goes, and you've just left with a 1 over cos x, yeah? Over u, but then you're multiplying that by, well, I've swapped 8 sine x dx for 4 du over cos x. Yeah. Now, what that's going to give you, if you multiply it into the top, is the integral of 4 over cos squared x divided by u. Or if you like, 4 over cos squared x times by 1 over u du. Yeah, you could think about it like that, because essentially we're doing, yeah, it's like if you times that up there, you get the 4 on the top and the cos squared x on the bottom. The du can sit here resting, and then you've got a divide by u, which is the same as times by 1 over u. Now, as u is 1 plus sine squared, but that's the same as u is 1 plus, now sine squared is cos squared x minus 1, isn't it? Sorry, 1 minus cos squared x. What am I doing? Sine squared is 1 minus cos squared. Yeah. In other words, what we can say is that cos squared x, if I add it over here and take that over there, is 2 minus u. And so sure enough, I get their answer then, 4 over 2 minus u times by u. And that's what they've got there. I've just got it looking the other way around. Yeah. So I've proved it. Okay, in the second part, we've actually got to do some integration and show that it's equal to ln a. Now, what were the limits here? I can't actually remember. I might even have to quickly, on my other screen, look up the actual sheet. 1 second. It's question 13, this, isn't it? Okay, let's just scroll down. It's just being a bit slow. Okay, here we go. Okay, it was between pi over 6 and 0, because I just cannot read that. Pi over 6 and 0, 8 tan x over 1 plus sine squared x. We'll start with what they start with. Don't rush. Okay, we already know that that is the same as 4 over 2 minus u times u du, but we've got to change the limits, and these were the limits for x. And remember that u is 1 plus sine squared x in this question. So sine of pi over 6 is a half, square is quarter, 1 plus a quarter is 5 quarters. Sine of 0 is 0, this is going to become 1. Right, we need partial fractions here. Yeah, you can only integrate that with partial fractions. So you're going to have to say 4 over u 2 minus u equals a over u plus b over 2 minus u. Yeah. Now you can use cover-up rule if you're super confident with this, great. But otherwise, make 4 equal to a times 2 minus u plus bu. Let u equal 2. You're going to get 4 equals 2b. In other words, b equals 2. And let u equal 0 next. That's what we're going to be doing next. Let u equal 0. And you can see that 4 equals 2a, and so a is 2. So it's relatively easy to split that into a partial fraction, and now we can actually integrate it. You're going to get integrate between 5 over 4 and 1, 2 over u plus 2 over 2 minus u du. That's the same as 2 ln u. Now the bottom doesn't quite differentiate to the top here. We need a minus 2 to lead with ln 2 minus u, and then we can just do it between 5 over 4 and 1. So that's 2 ln 5 over 4 minus 2 ln 3 over 4, because 2 minus 5 quarters is 3 quarters, minus 2 ln 1, which is 0, minus 2 ln 1, which is 0. So cross those out. And so the final answer should be, there's lots of ways of working this out. I'm going to take the 2 out. 5 quarters minus 3 quarters is going to end up being 5 divided by 3. And so I think the final answer should be ln 25 over 9, but I'm going to check that. Obviously, you can check this as well in the exam with your calculator. Yeah, that's a nice thing about it. You can definitely check it with your calculator. Yeah, it's right, good. Okay, the last question. Hurrah! We've got 3 terms of an arithmetic sequence. Now, what is an arithmetic sequence? It's something with a common difference. In other words, if we take the second term and subtract the first term, that should equal taking the third term and subtracting the second term. That is what this question's all about. Now we can use log laws. Sorry, made a boo-boo there. On both sides of the equation. Cool. Now we can ignore the logarithms, or if you prefer, exponentiate both sides. Try not to write it in the power as I'm about to do. Over 3 to the k minus 1. And now we can cross multiply. So we get 3 to the k minus 1 times 3 to the k minus 1 equals 3 times 3 to the k plus 5. Now, 3 to the k times 3 to the k does not equal 9 to the k or 9 to the 2k or whatever it is else you're saying. It equals 3 to the 2k because x to the a times x to the b, we simply add the powers. We don't times the x's together, we just add the powers. And it's the same here. So this is actually going to be equal to 3 to the 2k. That was a common mistake I kept seeing. So you get 3 to the 2k minus 3 to the k minus 3 to the k. Well, that's minus 2 times 3 to the k plus 1. And that equals 3 times 3 to the k plus 15. Okay, this is a disguised quadratic. You've got 3 to the 2k minus, by the look of it, 5 times 3 to the k, and then minus 14. Equals 0, yeah? We can now factorize that. Hope we can factorize it. It feels like we can. I think we're going to get 3 to the k. I think if I had u squared minus 5u minus 14, it would be minus 7 and plus 2. So 3 to the k minus 7, 3 to the k plus 2. Okay, that means that 3 to the k minus 7 is 0, in which case 3 to the k equals 7. And k is log base 3 of 7. Or over here, 3 to the k minus 2, equals minus 2, but that's impossible. And so that doesn't give you any solutions. Yeah, and if you try and write it, you'll write it as log base 3 of minus 2, but you can't log a negative number. Okay, there we go. And that is the end of the mock. Hope it was helpful, and yeah, good luck with your revision. Bye-bye.